The next session is mock lectures by our faculty members. They are here to give sample courses from their courses that you can have a feel of what the course is like at Osaka University. And also they will be introducing their own labs, so please enjoy. The first lecture will be by Professor MATSUSHITA Yasuyuki from the Graduate School of Information Science and Technology. His lecture title is Digitizing Reality, High Fidelity 3D Shape from 2D Images. Professor Matsushita, the floor is yours.
Thank you, Ariana-san. Hello, everyone. My name is Yasuyuki Matsushita. I'm a professor at the Graduate School of Information Science and Technology, Osaka University. My talk is about digitization of real-world objects, specifically about creating digital three-dimensional objects from two-dimensional images or photographs. Through this lecture, I hope you get some idea about how to generate photorealistic digital 3D shapes from 2D observations. "3D computer graphics is relevant in game and film industries. The objects in 3D computer graphics are often called 3D models. And 3D models are used for VR and AR applications. As on the left-hand side, which is a visualization of our building, there are also applications to digitally preserving cultural heritages, such as those Bayon temple, and for the purpose of archival and also digital preservation. And not only these, digital 3D models are useful for 3D printing and manufacturing. A conventional approach to generating 3D models relies on designers, essentially, using software to define points and planes in a digital 3D space. As you can imagine, the process is demanding and time-consuming. The newer and promising approach is to generate 3D models from 2D images, namely by recording a set of photographs of real-world objects and create the 3D objects by computation. So what is needed for digitizing reality? When we see an object in real world, what we are seeing is actually lights reflected off of the object's surface. We are not really seeing the objects, but what we are seeing is lights that are reflected. The appearance of real-world object is determined by a few factors. Reflectance, or object's material, which describes how well incident light is reflected. And incoming light, determined by surrounding environment of the object, and also the 3D shape of the object. Therefore, for the purpose of digitizing real-world objects, digitally measuring these three factors is important. In this lecture, let us focus on measurement of 3D shape of a real-world object. Let us begin with considering whether it is possible to estimate 3D shape from a single 2D image. Although we have a sense of 3D when we see a 2D photograph, mathematically speaking, it is impossible to determine the 3D shape just from a single 2D image. It is because a point on the 2D image can correspond to a set of 3D points in a 3D space. Let's say our viewpoint is C here, and we are now looking at the 2D point X on the image. We can draw a line, which is a 3D line from C to X, and extend the line further. The 3D point should be located on this extended line. However, only from this information, we cannot determine where the 3D point P is. To overcome this, we can rely on multiple images instead of a single image. Given a set of photographs recorded from different viewpoints, we can recover the 3D shape up to scale. So how do we do that? Let us walk through this computation pipeline. The first step for the 3D shape recovery is to identify corresponding points across 2D images. So, which is essentially, describing the same 3D points in different 2D images. Once we determine the correspondences, we can then recover the 3D points of these correspondences, and also the camera positions and the orientations where the photographs are taken. This computation block is called structure from motion. It already gives us a set of 3D points, however, they are rather sparse. To make it denser, we then apply another computation block. So from the known relative camera poses, dense correspondences can be computed across neighboring views because we already know which photographs are the neighbors. And this computation block is called Multiview Stereo. It provides us a depth map, as shown here, which describes how far the points are from each camera. With this computation, we can create a denser 3D point cloud, as shown here. Then once the dense 3D point cloud is obtained, the final step is to generate 3D mesh from the point cloud. It is a process of computing faces from vertices so that it can generate our watertight 3D shape. Okay. So now we looked at the 3D shape recovery method that takes images from different viewpoints. Another possible approach to 3D shape recovery is to use a set of images captured under different lighting conditions, but from a fixed viewpoint. So I believe you can see, lighting is varying on the left-hand side image. And from such images, we can compute the 3D shape like this in the form of surface normal. The surface normal is a 3D vector representing the surface orientation at each point. And in this visualization, surface normal vectors are color-coded in RGB channels. This approach is called Photometric Stereo, and it allows us to obtain a pixel-level detailed shape information. to demonstrate the strength of this photometric stereo, here I show a 3D shape recovered by the multi-view input images. Here I call it a geometric approach. And if we use a multi-light approach on top of it, multi-light approach is a photometric stereo approach on top of it, then we can add more details on the 3D shape. As you can see, detailed bumps are phase-free recovered by photometric stereo approach. Let me flip these two slides to observe the differences. Okay. Now we have seen two distinct approaches to 3D shape recovery. They have strengths and weakness. Multi-view stereo approach is good at recovering overall 3D shape, while the recovered shape may be a little bit coarse. Another nice thing about multi-view stereo is that it can produce the shape information as depth, which is very intuitive. On the other hand, photometric approach is good at recovering detailed 3D shape information. However, the recovery is in the form of surface normal, not the depth. So surface normal needs to be further transformed to create a 3D shape model. In fact, surface normal and the depth are related like this. So normal map is a gradient of depth map, which can be computed by differentiating the depth map. And if we integrate the surface normal, we can obtain the depth map. So they have this relationship. Now, let us take a closer look at photometric stereo. The setting is like this. So we fix a camera and is a target object and take a photograph under some illumination. Then we only move the illumination and take another photograph. So you can observe that the shading varies because the incoming light direction changes. So we continue doing this and take photograph until we are satisfied. And by analyzing the shading variation on the surface, we can compute the dense surface normal vectors as shown here. So this visualization, I put a reference sphere here. Just imagine that this is a sphere. Then the green color corresponds to a surface that is looking upward. And the magenta may be, looking right bottom direction. So this is called photometric stereo. The conventional photometric stereo relies on the image formation model, which is expressed by some explicit equation, here denoted as F. F is the image formation model. And this is for relating the measured intensity M, measured brightness M, and light source direction L, and also surface normal N. The problem of photometric stereo is given the measurements M and the non-lighting directions L, the goal is to compute the surface normal N by some optimization. As I mentioned, based on the image formation model F, we can compute surface normal. However, one issue is that the image formation model F needs to be manually designed, and it is not easy to reflect diverse materials that exist in real world as shown here. So again, in the conventional approach, the major bottleneck has been the design of this image formation model, F. To overcome the design problem in the conventional approach, we are working on developing a new data-driven method for 3D shape recovery. Namely, instead of manually designing the image formation model F, we use deep neural net to directly establish the mapping from the measurement to surface normal map. This approach naturally bypasses the handcrafted image formation model F, and by using the diverse data set, we can estimate the shape with diverse materials. And for doing that, we can train the network using the measured reflectances and computer-generated surface normal map. It's a computer graphics, and render the images and use them as a training data set. And this approach turned out to be quite effective for reflective materials. Here I show a comparison between conventional and the deep net-based approaches. So this is a conventional, and this is a deep net-based approach. The numbers below the surface normal maps represents the mean angular errors from the ground truth. As you can observe, the deep neural net-based approach can more accurately estimate surface normal, showing its strengths to adapt to real-world image formation model. So we also look at the case of unknown lighting. So far I have been assuming that the light directions are always known. However, in practice, it is not easy to calibrate the light directions. Therefore, we have developed a method that works even without the knowledge of light directions. This figure shows the network architecture of the method. And I'm not going into the detail, but it estimates the light direction on the first block, and it then estimates the surface normal. So here I briefly show the surface normal estimates from the input images with unknown light directions. Although it is qualitative, it can be observed that detailed shape information is obtained by the described method. So now my talk is almost over. In my talk, I talked about the topic of digitizing reality. We have learned two approaches to 3D shape recovery from 2D images. One of them is a geometric approach, which is good at recovering coarse 3D shape in the form of depth maps. The other is photometric approach, which is good at recovering detailed 3D shape, but only in the form of surface normal. We also have seen photometric stereo methods that are data-driven by the power of deep neural net, and it enabled us to work with diverse real-world objects. Thank you for listening. And finally, I would like to invite you to the virtual lab tour. Please start the movie.
Hello everyone, welcome to the Computer Vision Laboratory. I'm Cao.
I'm Yana.
Today, we would like to give you a brief virtual tour of our lab. I hope we can leave you some essential impressions about our lab's research and lives.
So let's go. First, let's have some talk with the international students in our lab. Hello.
Hi.
Can you please introduce yourself?
Yeah, sure. Hi, my name is Lee, and I'm currently pursuing my PhD degree in this lab. Previously, I obtained my master degree in robotics from NEST. I would like to briefly introduce my research here. Basically speaking, I'm working on point cloud, which is a discrete representation of 3D shapes. And we are developing theoretical foundations to better understand the existing algorithms and push them forward. So anyway, please consider to come here and join us. Thank you.
Thank you very much. Next, hello, Yang-kun.
Hi.
Can you please say something?
Sure, yeah. Hi everyone, my name is Yang, and now I'm a master's student in Computer Vision Lab of Osaka University. Yeah, and currently I'm working on photorealistic 3D reconstruction. Yeah, and previously I was an exchange student in Osaka University, and Osaka University offers a lot of interesting programs for both exchange students and the regular students in Osaka University as foreigner students. So if you want to come to Osaka University, please consider our lab to as a choice. Yeah, thank you.
Thank you very much.
So basically, our computer vision lab focus on 3D reconstruction, deep learning, and machine learning applications. We take photos of real-world objects and recover their digital 3D models.
Also, we work on plant vision, tackle problems in agriculture and also other industry with computer vision techniques. With this in mind, let's go to see something interesting. Hi, Makabe-san.
Hi.
Can you say something to the audience?
Hi everyone, I'm a second year master student, Makabe.
So, what have we been doing now?
I was scanning a 3D model, and this is a 3D scanner we have at our laboratory. And as you can see, it can record the 3D model of a real-world object in a really high resolution. And by the way, this is a special 3D marker, which allows the restoration between an image and a recorded 3D shape.
So, how do you make this object?
It's made with that 3D printer. In addition to the 3D scanner, we also have a 3D printer, which supports a two-color 3D printing. So you can create your own parts, making it easier to set up the real-world experimental environment.
Thank you very much.
Well, that's a really interesting 3D printer. Let's then take a look at the room behind me. Hi, Han. Could you briefly introduce what's this room for?
Hello everyone, I'm Henguo from MATSUSHITA lab. Along my side, this is dark room. So dark room, its name. When you close this curtain, then no light will come in. So inside this dark room, we have a set of devices for 3D reconstruction. So we have a camera and the LED light source. By control the LED and the camera, we can illuminate this object, you can see here. So taking these images as input, we can recover the object shape and reflectance. So we welcome you to join us and have fun in this dark room. Thank you.
Well, it seems we can take really impressive photos in this dark room. Let's see something else in our lab. Well, what's this moving object? Could you briefly give us some idea about it?
Hi everyone, I'm the first year master student. Our research focuses on autonomous robot as the application of 3D reconstruction and deep learning. We have two types of robot, a wheel robot and robot arm. These robots are equipped with RGBD camera and LiDAR for scene and object recognition. Wheel robots are used for evaluation experiments of autonomous navigation. And robot arms are used for development of automatic acquisition system for 3D scan. You can also use them to study other topics. Anyway, if you are interested in both computer vision and robotics, I think we can enjoy doing research together. Thank you.
So that's some research equipment in our lab. Apart from this, as you can see, in our lab, every student has their own desk and is equipped with at least 2 screens. So if you come to our lab, you can enjoy your research here. Please join our computer vision lab. We hope to see you in the future.
Thank you very much, Professor Matsushita, for the very interesting talk and the lab tour.